Alright, darlings, I hope this PowerPoint or video clip, whatever, proves helpful. It actually mega hurt today that we spent so much time trying to figure out how to do basic math. And I apologize because I just came from an AP physics class which doesn't even think twice when we have to deal with big numbers and multiplying and dividing and whatnot. So, let's brush up on math. So, we're talking about big numbers because we're talking about speed of light. Any speed is distance over time, right? So if we're talking about something sweet like this little car, it doesn't just go 5 meters per second, it can go 245 miles an hour, but what do? We just divide distance by time. And so if we talk about speed of light, you know that light is considered particles and waves at the same time. So particles are called photons. So when electrons in an atom jump from one level to another, they lose energy, and that energy is released in the form of photon. And photon is considered to be like a particle. And so if we're talking about speed of light, it's this huge number, which is usually referred to just as 3 times 10 to the 8th meters per second. So if you can imagine this super speedy particle called photon traveling 300 million meters per second. I mean, if you're into Harry Potter, that snitch is nothing compared to a photon. But the thing is that photon is not really a particle that is going to jump and just like zoom through the universe at that speed. Light is actually a wave. And it travels as a wave. It doesn't travel as little particles called photons. It's traveling as a wave. So when we talk about speed of light, we're not talking distance over time. We're talking wavelength. And wavelength, I hope you remember, is the distance between these two consecutive similar vibrations. So I can talk about two zeros, two consecutive zeros, or two consecutive troughs or consecutive crests. So as you see, this would be the longest wavelength, this would be the shortest wavelength, and this is the intermediate, like a middle. So red light is longer when it comes to wavelength in meters, and as we go into blue and violet, the wavelength becomes smaller, but what is increasing is frequency. Now what is frequency? So if we were to count how many vibrations this little pendulum is making per second, that would be our frequency. But that's, again, that's a particle or an object that is vibrating back and forth. When we're talking waves, we're talking how many waves per second are traveling through space. So that's what frequency is. And frequency is measured in something per second. So like oscillations with this per second, or waves, wavelengths per second. So it's 1 over second, or the same term is called hertz. So if when you are tuning your radio in the car to, let's say, 94.1, that's megahertz, like a million hertz. So get the joke at megahertz. Anyway, so all colors, all light travels with that huge, humongous 3 times 10 to the 8th meters per second speed. And since all colors travel with that speed, their wavelengths are different, and therefore their frequencies are different. So how do we figure out frequency of a light or wavelength of a light if we know wavelength or frequency? So for example, red light has a frequency of 4.6 times 10 to the 14th, or as it's written here, 460 times 10 to the 12th hertz. So how short, or how long, if you will, is the wave? So the formula for speed of light, C equals lambda times F, where lambda is our wavelength and F is our frequency. So we know frequency, and we need to figure out how long or how short the wave is. So we're looking for lambda. So then I take my C, which is 3 times 10 to the 8th, and I divide it by frequency, which is 460 times 10 to the 12th. So when you plug it into the calculator, you need to put it into parentheses. Or you can do 8 minus 12 is negative 4, and 3 over 460 is going to be 0.0065. Anyway, so Again, if you're plugging this into your calculator, you need to put parentheses around. Otherwise, your calculator is going to divide by 460 and then multiply by 10 to the 12th. It's going to be a totally different number. Because wavelength of a light is very, very short. So 6.5 times 10 to the negative 7th meters, that's the wavelength of a red light. Now, what if I know the wavelength and I need to figure out frequency? Again, C equals lambda times F, so from there frequency is going to be speed of light divided by the wavelength. Speed of light is again 3 times 10 to the 8th. The wavelength is given as 530 times 10 to the negative 9th, and that's what I'm writing in here. So that will give me 5.7 times 10 to the 14th hertz. Again, you need to parenthesize this denominator. Otherwise, your calculator is going to divide by 530 and then multiply it by 10 to the negative 9, and you're going to get a different number. So let's compare. We have these numbers. We have 530 times 10 to the negative 9th meters and 5.7 10 to the 14th hertz. For red light, we have 6.5 times 10 to the negative 7th meters and 460 times 10 to the 12th hertz. Now these numbers are kind of different, but if you take a close look, 530 times 10 to the negative 9 is the same as 5.3 10 to the negative 7th. What I did is I made the number 530 100 times smaller, and it turned into 5.3, and I keep my 2 sig figs, so I'm good. So 5.3, and since I made my number 100 times smaller, my power of 10 is going to be 100 times higher. So instead of negative 9, it's negative 7. On the other hand, if I have 6.5 times 10 to the negative 7, I can turn this into negative 9. And so I just made my power of 10 100 times smaller. Then my number, which was 6.5, needs to be 100 times higher. So I get 650 times 10 to the negative 9. Now let's look at our hertz. 5.7 10 to the 14th is the same as 570 times 10 to the 12th. You can think about it. I multiplied by 100. So I dispensed second power from here and turned it into 2 decimal places. Now 4.60 times 10 to the 12th, if I put this into scientific notation and turn this into 4.6, my power of 10 has to be 100 times bigger because I just made this number 100 times smaller. So 4.6 times 10 to the 14th. And then, as you look at these numbers, green light is shorter, but it has higher frequency. Red light is longer, but it has a lower frequency. Longer and lower frequency. So frequency, as frequency increases, lambda or wavelength decreases. Shorter waves have higher frequency. Longer waves have lower frequency. So again, visually, red light is longer and less frequent. If you look at the time, we only have 1, 2 crests. And then green light is shorter, but frequency is higher. We have almost 2.5 waves in here. And then blue light is even shorter and then more frequent. You have 1, 2, 3, almost 4 crests that fit within the same amount of time. So as your frequency increases, the wavelength decreases. As your wavelength increases, your frequency decreases. They are what is called in math inversely proportional. Now, light carries energy. And energy is measured in joules, but not in these kind of joules, in joules after a scientist. So, as a light is emitted, what happens is electrons, as I already said, jump from a higher level to a lower level, energetic level. And you know all those levels we talked about before. So it dispenses of energy that is contained within an atom in the form of light energy or in those photon particles. And then the amount of energy depends on how many levels it jumped. You can think about it, you can jump through 2 steps as you run down, or through 5 steps. Obviously, when you jump over 5 steps, you kind of, the impact is huge because you're losing a lot of energy in one leap. The same thing with electrons. the more energy levels it jumps, the more energy is going to get rid of. And also, the light that is emitted is going to be different in color, in other words, in frequency. So the amount of energy can be found by multiplying what is called Planck's constant, which is a constant, so therefore it's always the same number, 6.63, and it's a very small number, 10 to the negative 34th joules times seconds. So we can always figure out the amount of energy carried by a certain color if we know its frequency, and all we need to do is just multiply it by Planck's constant. So for example, if we already talked about red light and green light, which one of them is going to be more energetic? So just by looking at these numbers, I hope you can figure out that green light is going to be more energetic because it's higher in frequency. You can think about it, it's going to come in, if you roll back here, there's going to be more waves coming in within the same amount of time, and each wave is bringing a certain amount of energy. So, but just algebraically. So if I were to figure out how much energy green light carries, that would be 6.63 times 10 to the negative 34th, that's our Planck's constant, times frequency, and I end up with 3.38 times 10 to the negative 20. What I did is I just multiplied 663 times 5.7, and then I looked at 10 to the negative 31st and 10 to the 14th, and negative 34th and 14th gives me 10 to the negative 20. And then to get this into scientific notation, I do 3.8 times 10 to the negative 19th. Now, if I were to find the amount of energy carried by red light, that would be 6.63 times 10 to the negative 34th. Again, 4.6 for frequency. And that gives me 30.4 times 10 to the negative 20, or 3.0 times 10 to the negative 19th joules. So red light is longer, less frequent, and I mean its frequency is lower. So, and therefore it carries lower energy. Think about this: when something is not very hot, you need infrared light to see it. It's not very hot, it's not glowing, but you can still detect it if you have infrared goggles, and you can see it at night. But if something is very, very bright, you don't need infrared goggles. You can see it glowing because it's very, very hot. And the sun, if you think about it, ultraviolet, we need protection from ultraviolet radiation that is coming from the sun because it's very, very energetic. All right, so the higher the frequency, the more energy it's carrying. And when you talk about flames, blue flame is actually more energetic than red flame, even though we kind of relate blue as kind of cold colors versus red, but that's actually the other way around. Anyway, what we did today in the worksheet for you, just to go through it one more time. So if we were to figure out the wavelength if we were given frequency, so wavelength, we take C over frequency. C is 3 times 10 to the 8th. Or if you want to be strict with sig figs, I can give you speed of light in 5 sig figs versus 3. So, but if you look at the numbers, it's by 1 meter, big deal. Not even 1 meter, it's 1 times 10 to the negative 7th. Anyway, so 2.311 times 10 to the negative 7th meters. And then 2.310 times 10 to the negative 7th meters, depending upon which sig figs you're taking. But again, you take your C and you divide by frequency, and that gives you your wavelength. If I have 2.310 times 10 to the negative 7th, I can move my decimal 2 times and end up with 231.0 times 10 to the negative 9th. And 10 to the negative 9th, the scientific notation for it is nano. You can think about nanotechnology is about something very, very small. So 231 nanometers is going to be my wavelength if frequency is 1.2976 times 10 to the 15th. I take speed of light, divide by frequency, and I get my wavelength. What if I have wavelength? I need to figure out frequency. My wavelength right here is given in nanometers, so I need to turn this into meters, and nano, again, is 10 to the negative ninth. Very, very small. So 3 times 10 to the 8th over 650 times 10 to the negative 9. What I did is I just did 3 over 650. That gave me, my calculator gave me 0.0046. 10 to the 8th over 10 to the negative ninth. When you divide, you subtract the power of 10, right? And it's already negative 9. So therefore, it's going to be 8 minus negative 9 is plus 9. So 8 plus 9 is 17. And I can turn that into, I move this 3 places. So from 17, I get to 14. So 4.6 times 10 to the 14th. Or if you remember, we can even do it as 460 times 10 to the 12th hertz. And then number 3 in your worksheet, we were supposed to figure out the energy needed. Again, it's going to be Planck's constant. And just to be strict and give you 4 sig figs, I turn this into 4 sig figs. Instead of 6.63, I'm giving you 6.626 times 10 to the negative 34th. And here's our frequency. Multiply one by the other. If I just do 6.626 times 1.081, it gives me 7.163, negative 34 and 15. I add these two guys and I end up with 10 to the negative 19th joules. And that's it. So I don't know, hopefully this helps a little bit. If you need more help or more practice with plugging numbers into your calculators or manipulating a simple formula, I can see you in back work. Or you can watch this video one more time or practice, and hopefully it will get easier.